Good morning, my dear students. So, in this lecture video, I am going to take on another a new different problem, that is problems on uniform distributed load. Okay. So here in this problem, both the elements. So here in this problem, we are going to consider the two elements. Both the elements are carrying what UDL. How to solve such type of problems. Okay. So here this syllabus already told you. Okay. So here the coming to the problem. So look at the observe the diagram here. So here that this is the beam element. Here and this beam element. So this is the load is uniform distributed load is acting 12 kilonewton per meter, but here from this element at element number 2 the load is acting little bit higher than this. Okay, that is the double of this, that is 24 kilonewton meter. Okay, kilonewton per meter. Okay, so length for the first element is they given what the 4 meter. So second element length is also they given 4 meter. Okay, but at node number 1 that is at middle is completely fixed. At node number 2 it is a roller support. At node number 3 is also a roller support. Okay, so here we have to delete what the v2 v3. You need to calculate only the theta 2 theta 3. Okay, so that is what from this diagram explanation. Okay, so here read the question first for the problem number 3rd. Okay, for the beam below as shown in the below figure, determine the end reaction. Okay, so you have to calculate the end reaction also here, and the deflection at midpoint mid span. Okay, so it is a little bit lengthy problem. Okay, they are asking both reaction and what the mid span, the maximum deflection at mid span. Okay, here. Okay, so calculate the Young modulus E is equal to 200 gigapascal and moment of inertia I is equal to 2 into 10 to the power of 6 mm to the power of 4. Okay, so I already told you in the previous lecture, first step is what you have to convert this gigapascal into what kilonewton per meter square and m to the power of 4. Okay, so how to calculate, I told you. Okay, E is equal to 200 Newton per mm square is given, means 2 into 10 to the power of 5. So you make it 10 to the power of 5 into 10 to the power of 6 by 10 to the power of 3, which is equal to 2 into 10 to the power of 8 kilonewton per meter square. Okay, so once I is equal to and I is equal to 2 into 10 to the power of 6 is there, so meter is there, so 10 to the power of 3 you have to take. Okay, so finally you are going to get 4 into 10 to the power of minus 6 m to the power of 4. Okay, so EI is equal to what? So multiply this to this, you are going to get 800 kilonewton meter square. Okay, so almost in all the problems you are going to get the same values. Okay, so I told many times the problems question is similar for the all the problems, but the diagrams or the beam element in the given questions are different. Okay, so here the from point 1 to here they are acting what the 12 kilonewton per meter UDL, and here 24, double that double than this. Okay, you need to calculate what end reaction and deflection at mid span, that you need to calculate from the given beam element. Okay, so here the first step is same for the how you did in the earlier. So look at the draw the free body diagram or FA model. So here at draw the horizontal line, this is the beam element from node number 1 to 2. So v1 theta 1 f1 m1, so v2 theta 2 f2 m2, and v3 f3 theta 3 and f3 m3. Okay, so here the rotational angles are what theta 1 theta 2 theta 3. Okay, so length element 4 mm, they given 4 mm for the both the element. Okay, so here completely fixed, so v1 theta 1 will become 0 at node number 2. So v2 is become 0 and v3 is equal to become 0. Okay, so you need to calculate the theta 2 and theta 3. Okay, so these two you need to calculate here. Okay, so how to calculate? With help of formula, we have the formula, the stiffness matrix for the beam element is equal to what? K is equal to E by LQ. So this formula we have. Okay, so since here the element for the both the element is 4 is there, so calculate the E and EI becomes same. Okay, so EI by LQ is equal to what? 2 into 10 to the power of 4, and multiply those two, you substitute the E and I value, so you are going to get 12.5. Okay, so after calculating this 12.5, that is what EI by L cube ratio, then you go for calculating the element stiffness matrix for each element. Okay, so here the first element, so EI by LQ already calculated this 12.5. So for first element length is what? 4 is there, substitute here 4. So 12 6 into 4 24, like that you have to calculate. Okay, so wherever L is there, substitute 4, so you are going to get this. Okay, both since the length are both elements are same, so you are going to get same values, but the degree of freedom will be changes. Okay, so for first element v1 theta 1 v2 theta 2, and the second element v2 theta 2 v3 theta 3. Okay, so similarly calculate the global stiffness matrix. Okay, K is equal to K1 plus K2. So here since the maximum node is 6 is there, that is theta 3 is there, so v1 theta 1 v2 theta 2 v3 theta 0, so you are going to get 6 into 6 matrix. Okay, so how to add this, I already told you in the previous lecture video, that is v1 is equal to v1. So this 12 I wrote means v1, so v1 check in the both the matrix here. So here this is v1, so v1 is not there here. Okay, 12 plus 0 equal to 12. Okay, like this here second 24, how I wrote 24 here means v1 24 is there, here also v1 24 is there, so check it here. So v1, this is, look at this v1, actually this is a theta 1, this is not a v1. Okay, sorry, this is theta 1. Okay, so theta 1 v1 check it, theta 1 v1, so here theta 1 v1 24 is there, here not there, 24 plus 0 24. Okay, like that you have to form this global stiffness matrix with the help of the individual element stiffness matrix. Okay, so after calculating this, you need to calculate the nodal displacement factor. So these are the nodal displacement factor. Q is equal to v1 theta 1, v2 theta 2, v3 theta 3. Okay, so since the given problem is belongs to the UDL, so uniform distributed load formula we have already derived this equation. F is equal to P naught LE by 2, P naught LE square by 12, P naught LE by 12. Okay, this is the formula is there being due to uniform distributed load. So for the first element you need to calculate. First element is uniform distributed load is 12, second element is 24. Okay, calculate the separately. So since for the first element P naught is equal to minus 12 kilonewton, substitute in that equation, you are going to get this. Okay, so that is finally you are going to get the at a node for the first element v1 theta 1, v2 theta 2 is equal to minus 24, minus 16, minus 24 plus 6. Okay, similarly calculate the second element. So P naught is equal to minus 24, L is equal to 4. Okay, substitute here all these values in the second equation, you are going to get this. Okay, so finally you have to add this F1 and F2. Okay, so if you add F1 and F2, that gives the global force factor. Okay, so F is equal to finally you are going to get minus 24, minus 16, 72 and 16, 48, this what 32 minus. Okay, so after calculating the global force factor, you have to substitute the equilibrium condition, that is Ku, which is equal to F. So this K value already calculated here. Okay, substitute the K value in this equation. So V1 displacement, V1 theta 1, V2 theta 2, V3 theta 3 and the force value. Okay, so now you apply the boundary condition. Okay, in the node number 1 it is no at okay, at node number 1 is completely fixed, so you have to delete the first row, first column, that is V1 you have to delete at this one and this one. Okay, at the second column ruler support is there, that means the V2 will be 0. This is V1 theta 1, this you have to delete this third row also. Okay, V1 and again this also you have to delete. Okay, that is fifth row. So remaining you have to note down. Okay, so why I deleted here, because this is a boundary condition. Okay, so they in the question they given. Okay, so remaining you are going to get, that is 128, 32, 32, 64, that is theta 2, theta 3. Okay, on simplification you are going to get theta 2 is equal to minus 0.0228 radian and theta 3 is equal to 0.0514 radian. Okay, so these are what the displacement how we calculated by applying the boundary condition. Okay, so they are asking also to calculate the maximum deflection, means we have the formula already. Okay, so this V is equal to H into Q, so where H is equal to Hermite shape function, their values you have to note down here, and zeta is equal to 0, substitute in this equation. Already we calculate the displacement value also. Okay, so here substitute this equation, so you are going to get the what the maximum deflection at midspan is equal to 0.5, 0.125 length. Okay, LE, so 0.5 minus 0.125. Okay, so for first element, so here you calculate the individual deflection. So for first element length is 4, V1 theta 1, V2 is 0, so substitute here. So finally you are going to get the deflection for the first end reaction is what the end deflection is 11.4 mm. Okay, like that similarly you have to calculate the second element. So second element deflection is equal to minus 37.11. Okay, so this is what how we need to calculate the deflection for the separate element V1 and V2. Okay, so in this problem they are asking reactions also, so it can be found by using the relation. We have the same by using elimination method. We have the formula R is equal to KQ minus F. Okay, so in this problem for the first element V1 theta 1 V2 is equal to 0, so consider these elements are 0, so substitute values here. Okay, R1, R2, R3, R4, so 12.5 substitute here. Okay, so this is the K value, this is U value, this is F value. So first you multiply this to this. Okay, so you are going to get the single values, again you subtract from these values to this, so you are going to get the reaction like this. So R1 is equal to 17.16, R2 is equal to 6.88, R3 is equal to minus 30, R4 is equal to minus 34.4. Okay, that is for first element. Second element is equal to V2, V3, ruler support is there, so V2, V3 is equal to 0. So after writing this, okay, so again same procedure you have to follow. So again you have to do the multiplication here. Okay, this into this, you are going to get single values, then you subtract these from this values to this, you are going to get the final answer like this. Okay, that is R3, R4, R5, R6, that is R3 is equal to 56.58, so 34.32, R2, so R5 is equal to 32 and R6 is equal to 0. Like that you have to solve the reaction and all those things. Okay, so here reaction we already used this formula in the elimination method. Okay, in the while solving the previous problem, same formula you have to use, but here you have to apply the conditions. Okay, no need to calculate R1, R2, okay, they are asking the what the end reaction. So wherever fixed is there you have to delete, so remaining you have to note down here. Okay, so in the force value, okay, Like this you have to calculate. So in this problem, what is the difference between the previous problem and this problem means here the UDL, both the element consist of UDL, so you have to add the both the forces like this. For you calculate the separately force due to UDL, force due to UDL, and combine you are going to get the final force. This value take in the global equilibrium condition. Okay, in the previous case what you did is so only the single load is there. Okay, so you are going to not going to add this force factor in the previous case, but here you are going to add. So this is the change will be there, so remaining procedure is same. Okay, as usual what you did in the previous problem. Okay, so like that you have to solve the uniform distributed load when the beam is having the what UDL load. Okay, so here you have to add the force, this one and this one combined, that force total global force factor you have to use in the equilibrium condition. Okay, so like that you have to solve the problems on UDL. Okay, so I hope you understand this problem. Okay, thank you.